because I would like this to be more interaction presentation. So this is the outline of my presentation. I'm going to talk about road safety advancements and challenges, just to remind you of where we are. And I would like to give brief background about this new era that we are entering, which is the era of smart mobility and big data. And I will show you applications of how we can use this new era of smart mobility and big data in several new road safety applications. I'm going to talk about real-time identification of crash-prone locations, dynamic identification of safest routes to destinations, the real-time optimization of traffic safety of corridors and networks. I'm going to talk about modeling road user interactions and organized and less organized traffic environments. And during these applications, I will be giving examples and case studies using actual applications. So I'm sure you all know, and you don't want me to repeat that, it is very important to reduce the social and economic cost of collisions. The importance of reducing these costs cannot be overstated. We have 1.35 million people killed every year, and we are the only profession, transportation engineers, that have a product, and this product is the road network, that is associated with 1.35 million fatalities and 50 million injuries. And we have been getting away with it for the last 50, 60 years by blaming the road user. There is some good news, especially in developed countries. Between 1970 and 2005, there has been significant reduction in road fatality rates, despite a considerable increase in traffic volume and vehicle use. So this is really good for developed countries. Although the picture has reversed and we don't have this reduction anymore. However, associated with these advances are a group of challenges that will complicate the future direction of road safety if we don't change our approach to managing road safety. These challenges will make it difficult to achieve further advancements in reducing traffic fatalities and injuries. And in my opinion, these challenges are the reason for the smaller reduction and in many cases increase in road fatality rates in recent years. If you look at the existing number of traffic fatalities, the 1.35 million, it is about 12% higher than the number we started with in 2010, when the first UN Decade of Action for Road Safety was announced. Since 2015, even in developed countries, the reduction in fatality rates has slowed down significantly. And many countries, developed countries, are showing a reversal. They are showing an increase in fatality rates now. If you look at the US as an example, the US road fatalities spiked by 20% in the first half of 2021. This is the largest increase ever recorded in its reporting system's history. We had about 20,000 people killed in motor vehicle crashes during this period. So the advancement and the reduction that we have seen from 1970 to 2005 is seeing a reversal now, and we need to act on it. So what are these challenges? Some of these you may know already. Reliance on collision data is reactive and has fundamental ethical and practical issues. A significant number of collisions need to be observed, which we will subsequently strive to prevent. So basically, stated bluntly, as I say, we need to have fatalities and injuries first to justify funding safety improvements to reduce future injuries and fatalities. So to spend money on improving safety, we need to identify locations as black spots, which means that these locations should have fatalities and injuries, which doesn't make a lot of sense. The second one is that the difficulty of evaluating the effectiveness of newly installed safety treatments within a reasonable time period. We're using 3-5 years of collision data. And because we cannot tell quickly how effective a new safety treatment is, practitioners are being discouraged from experimenting with innovative but untested safety treatments. We don't try new things because we will not know how safe or how effective they are. So there is a need to evaluate safety over shorter time periods, not 3 years, not 5 years, not even a month. We need to go for much shorter time period. So what is the good news, if there is any? Yes, there is, in my opinion, very good news. The good news is that we are on the cusp of a new era of smart mobility. And by smart mobility, we're talking about the application of information and communication technologies, which will lead to interconnected road infrastructure, travelers, and transportation modes, leading to higher safety, enhanced mobility, and minimum impact on the environment. New technologies such as connected and autonomous vehicles are expected to provide considerable social and economic benefits. However, in my opinion, the biggest benefit will happen from big data. The expanding use of information and communication technology in transportation will allow the collection of huge, unprecedented volumes of data across all transport modes and systems. So according to a new study from Morgan Stanley, for example, autonomous vehicles are expected to generate as much as 40 terabytes of data an hour from cameras, radar, and other sensors. And these can completely change the way we evaluate and manage safety, something we could not do in the past. So why this big data is important? Because as I said, we have over the last 50, 60 years, we have relied on aggregate collision data for 3 to 5 years. However, a more effective approach to safety management will require evaluating safety of different networks over much shorter time periods. We're talking about minutes or even seconds to dynamically change the traffic environment and optimize safety in real time. This is a methodology that departs fundamentally from the past 50 years of reactive safety management. We're going to rely on safety surrogates, not on collisions. And the main input to the new evaluation methodology will rely on road user trajectory. And it can be used with data sensors or connected and autonomous vehicles. It can come from cameras, from LiDAR, infrastructure-based LiDARs and cameras, or from the autonomous and connected vehicle as they move, which is becoming available. Many of the data is currently available and we can use it now, but we don't have the techniques that will allow us to mine and understand the data. Another huge benefit, and this is my opinion again, is that this real-time safety evaluation will allow us to resolve the conflict between mobility and safety. Historically, road transportation has mainly involved the consideration of two main values, mobility and safety. In the past, these two values were always in conflict. To improve safety, you need to restrict mobility. Why? Because the higher the mobility, the higher the exposure to collision risk. So most of the safety countermeasures were always targeting reduced exposure, no left turns, no right turns on red, and so on. In my opinion, again, the use of advanced technology and the availability of big data and the use of surrogate safety measures, not collisions, for real-time optimization of transportation networks can resolve this decades-old conflict between mobility and safety. So I'm going to share with you some three main applications where I feel that this big data and this new era of smart mobility can make a big difference for safety. The first one is the real-time safety evaluation of road networks using big data. I'm going to show you different applications of real-time safety evaluation, the dynamic identification of crash-prone locations, dynamic identification of safest routes to destinations, real-time optimization of traffic, and how we now modeling road user interactions in both organized and less organized traffic environments, which is giving us much better understanding of collision failure mechanisms and how safety measures actually work. So let's start with the first application, real-time safety evaluation. What do we mean by real-time safety evaluation? Real-time safety evaluation will estimate the real-time crash risk from dynamic traffic data that are updated within a very short time interval. This was not possible 10 years ago. Now it is available because of recent advances in sensor technologies, such as edge cameras, LiDAR, and connected and autonomous vehicles. And these are resulting in large amount of real-time traffic data, which we can use for real-time safety evaluation. The real-time safety evaluation has been there for a long time, and researchers have done that over 20 years. But in my opinion, most of the existing real-time safety models rely on historical collision data. So we're doing regression analysis again. We take collisions, and we have a binary logistic model, crash or no crash. So these rely on collision data again, which is problematic, as I said from the beginning. Not only that, these models, existing models, and there are a lot of work in Florida and actually in China, many people, many researchers are using these models, crash-based real-time safety evaluation models. And they don't reflect how risky the safety level is. A better approach is using traffic conflicts, in my opinion, extracted from real-time road user trajectories, plus dynamic traffic parameters as an intermediate for crash risk prediction. Let me show you an example of some of the work we've done with data, autonomous vehicles data from lab. So this is a case study from lab, a corridor in Palo Alto, California, and using 3 months of autonomous vehicle data. The corridor had 9 signalized intersections, as you can see, and there is an autonomous vehicle going through the corridor back and forth. So we take this data generated by the autonomous vehicle and extract all the vehicle trajectories, not only for the autonomous vehicles, but the surrounding vehicles as well. And from these trajectories, we extract traffic conflicts. We do geospatial grouping of conflicts, and we can also do temporal segmentation of conflicts, and then we can model that to get the real-time crash risk. So that's the corridor, and you can see the conflicts changing in real time. And then what we can do is that we can take these conflicts, and there are several techniques that we can use, all based on extreme value theory, and I really like this approach, because it offers a realistic way of going from trajectories and conflicts to crash risk without using regression and modeling a crash, no crash, based on historical information. So in this case, you see that these are all the conflicts, and we're using one conflict indicator in this case, which is the time to collision. We take the extremes, and this approach is called the block maxima approach. So these red dots are the maxima or the extreme conflicts within each time interval. We fit an EVT model in this case, and we can use that to extract crash risk from conflicts. Another approach is what we call the peak over threshold approach. And again, this threshold can vary, and it can be a function of many covariates. And in this case, we will have a generalized Pareto distribution. And again, we can use that to for real-time safety evaluation of corridors and locations. So this is the EVT on your right, and this is the negative of one indicator. In this case, the indicator is the post-encroachment time. And because it is the negated value, so this dashed area to the right is the crash risk. And it works very well. So we can even validate this approach with aggregate actual crash risk. So in this case, we have 4 locations in Surrey, British Columbia. And for each location, 4 figures and 1 location each, you see different conflict indicators, MTTC, modified time to collision, PET, post-encroachment time, drag, deceleration rate to avoid a crash, and so on. And for each one, the green horizontal line is the observed number of collisions, and the red dot is what we are estimating from this aggregate crash rate over a year. And you can see that the model works extremely well. So we can go from vehicle trajectories and conflicts to actual crash risk. But the beauty, what I really like about this approach, is that we can do real-time safety evaluation. So in this case, we defined 2 real-time indicators from the EVT distribution. One is called crash risk, which is only positive when there is a risk of a crash. The other one, which in my opinion is more useful, the return level, which fluctuates. So it offers a value that can reflect how risky a situation is. So in this case, you can see we're using different indicators, the time to collision, the post-encroachment time, drag, and for each indicator, there are 2 real-time metric. One is the crash risk, one is the return level. And you can see that for these are 4 intersections, it varies in time, and we can use that to evaluate the real-time safety of a location. Not only that, we don't have to rely on only one conflict indicator. As our research at UBC has shown that each conflict indicator represents only a partial severity image of traffic events. It doesn't tell you everything. We need to integrate. And you can see this figure at the bottom, which is showing you how many conflicts are identified using different indicators. And you can see that each indicator identifies different conflicts, not only in number, but the conflicts themselves are different. So our recent work, actually, which is done by one of actually a Chinese researcher, Fu, and he's showing that we can combine these indicators and get a real-time multivariate real-time metric. In this case, this is the crash risk. And in this case, we're using 2 indicators, the modified time to collision and the post-encroachment time. So this is a combined crash risk and joint return level from 2 indicators. And of course, I can do 3 or 4 and so on. So this is going back to the corridor in California. You can see that we can evaluate the safety of the corridor, intersections, and segments. And you can see how we can change these in time, and we get very good evaluation of the safety level. This is the same corridor. We can identify the dynamic traffic collision-prone locations, and these are changing in time. And you can see that the conflict and the heat map and the crash risk, it changes in time, and we can identify different areas depending on the dynamic traffic parameters. So in this case, as you can see, we have, this is downtown Athens in Greece, and you can see that these are changing in time. So this is the map of downtown Greece, and you can see that these are the intersections. The vertical axis is time, and you can see that intersections safety level varies in time. So what is collision prone at time 1 is different than what's collision prone at time 2, time 3, and time 4. And we can change that by making changes to traffic control, mainly, to minimize the adverse safety impact of traffic operation. So this is an interest. This is again downtown Greece, downtown Athens, sorry. And you can see how intersections safety level is changing in time, from time to time. So they can be green, and they can switch to being red and yellow. And I can also aggregate this information. I don't have to only apply traffic control safety improvements. I can aggregate this information and end up adding a left turn lane or adding a right turn lane. So I can still go for the high-level countermeasures in addition to making dynamic traffic control change. So how would you improve the safety of these dynamic crash-prone locations? In general, safety improvements at the identified crash-prone locations can be undertaken by making changes to traffic control, phase changes, variable speed limits, ramp metering, etc. Or it can also be done at the network level. In this case, it will be signal offsets, rerouting, which in my opinion carries a lot of potential. And this real-time safety optimization can lead to significant safety benefits that cannot be achieved through the traditional current reactive safety management approach. Let me give you an example of some of the work we've done on taking signalized intersections and optimize the operation of the signal for safety. So these adaptive traffic signal controllers have existed for a long time to minimize vehicle delay. But very few efforts, if any, were undertaken to optimize safety in real time. And if you remember, for the first time, we have something like this. So if you look at the bottom figure, the joint return level, we have a safety level that fluctuates in time. And I can use that in the optimization process to minimize this safety level, this crash risk. And by doing so, I will minimize the number of crashes that will occur at the signal. So again, you can see that we use both, but I prefer to use the RLC, which is the return level on a cycle, because it is a continuously changing safety level that I can use for minimizing crash risk and conflicts. And I can train the controller using AI techniques. In this case, we are using a technique called reinforcement learning. And you can see in this case how the shock wave area as the approach to the intersection is changing as the algorithm is learning how to minimize safety risk. So I think at episode 530 or something, you can see that we have learned, the controller has already learned how to minimize crash risk and how to minimize average shockwave area. If you look at how much safety benefits you will get from this optimization, and this is the cumulative number of conflicts, and you can see that. Was that a question? Okay. So you can see that we are getting significant reduction in the number of conflicts by this optimizing road safety as a signal in real time. Another work that we're doing that I'm really think that it would be very important is what we call the signal vehicle coupled control. And the one that I just showed you here, we are optimizing the traffic controller operation. But we can also adjust vehicle speeds and vehicle trajectories to minimize crash risk. So I can have a coupled control. So this signal vehicle coupled control, it controls two things. It controls vehicle trajectories, but it also controls signal timing. So modifying vehicle trajectory acts as a multiplier. So, and to the best of my knowledge, this is the first SVCC developed for safety that can be applied in real time and uses actual crash risk, real-time crash risk. So in this case, we use what we call soft active critic RL algorithm, reinforcement learning algorithm. The inputs are estimated conflicts on each approach using a model, and also the time and phase and the vehicle coordinates. We are assuming that we know the coordinates from connected or autonomous vehicles, or even from cameras, edge cameras. The reward function that we're trying to minimize is the sum of traffic conflicts on all approaches. So this approach will issue speed advisories to vehicles within a range on each approach and uses connected vehicle data to identify key variables. This was applied to two intersections. As you see, both are in Surrey, British Columbia. And we tested different scenarios. And you can see that on the right are the traditional vehicle trajectories at the intersections. And on the left, you can see how adjusting vehicle trajectories and providing speed advisories has resulted in significant reduction in shock waves in this case. So we can really improve safety by doing both traffic control optimization and vehicle trajectory optimization. And you can see here that we are achieving about 40 to 50, in some cases 60% reduction in traffic conflicts. And what we found is that at high volume intersections, the signal optimization is more important. While at low volume intersections, the trajectory optimization will be more important because of the low volume. I want to make sure that we do not develop shock waves and a lot of conflicts between different vehicles. We can also, we don't have to optimize safety alone. We can optimize safety and mobility at the same time. So in this case, I'm showing you that we can have a multi-objective optimization of safety and mobility by applying a weight. And this weight, let's say that the weight goes from 0 to 1 for safety, and it will be 1 to 0 for mobility. And you can see that depending on the weight, if you go 100% safety, which is the right of the figure, you can see that the conflict will be reduced significantly, but not the delay that much. and the other way around. So we can apply a weight to mobility and safety in one multi-objective optimization of the signal control. The third application I would like to share with you is multi-agent modeling of road user interaction. And as I said, I remind you, all of these applications are only possible through big data that did not exist before. A lot of people have been doing simulating traffic safety using programs such as SSM. Some of you may be familiar with SSM. That actually was mainly developed at UBC long time ago. And the problem that it never worked, and you can still see papers today using this SSM model with VISM, for example, to estimate conflicts. And they claim a reduction in conflict and that something really works. The problem that SSM doesn't work, even so we developed that. And for two main reasons, is that VISM parameters, micro-simulation model parameters such as VISM, they are not calibrated for safety. They are never. And there have been methods, including Professor Yanyong here, that worked on calibrating the road user behavior parameters for safety. So we will take actual conflicts and we will take simulated conflicts and try to minimize the difference by adjusting road user behavior parameters. Still, even so, this is an improvement. The results are not totally realistic. And if we're going to simulate safety, especially simulating new countermeasures that we haven't implemented yet, we need a more realistic and better modeling of actual road user behavior and collision avoidance mechanism. With advancement in AI, we can do that now. So our recent work is using Markov game approach to develop a simulation framework for modeling road user interactions and their collision avoidance mechanism. And I will show you some examples. This is an intersection from Shanghai, and you can see how this pedestrians will run when the vehicle is doing a right turn. So this is an interaction. Can we use AI to duplicate the behavior of the two road users in this particular interaction? Would a simulated pedestrians run, or would the vehicle stop? What will happen if I try to duplicate this behavior? This is an example from the same intersection, and you see the motorcyclist that is swerving around other objects. Can we model that and duplicate this exact behavior in the near miss? Yes or no? And the simple answer is yes, we can. So in this case, we use multi-agent modeling of road user interactions. We use a utility-based micro-simulation model. So road users in this case are modeled using multi-agent reinforcement learning as rational decision makers that attempt to maximize their utilities over time. So we have a utility function that will be maximized. The utility is represented by a reward function, and this reward function is extracted or recovered from actual examples of near misses. So we feed the program with many near misses or many interactions, detailed interactions, and the AI approach, this approach, the adversarial inverse reinforcement learning approach, will learn and can duplicate the behavior. So let's see whether we can do that or not. So we take the videos and we do, it has to be very accurate. So using things like YOLO 3 and box tracking may not really give you good results. We have really to go for very detailed, accurate evasive actions, swerving, yaw rate, acceleration, deceleration, and the like. So we extract all of this information. In this case, this is an interaction between a vehicle and a pedestrian. And we go through this approach. I don't think we have the time to describe what the approach, how it works. But anyway, It is adversarial inverse reinforcement learning approach, where we have two networks, a critic network and actor network, and we try to recover to the extent that we cannot differentiate between the two. So this is an example of simulated and actual trajectories. And you can see that we can duplicate the trajectories with very high accuracy. And this is really good. So when we simulate safety in the future, we simulate it based on realistic actual road user behavior. Not only that, so in this case, I'm showing you a group of near misses that we use to test the simulation model we have. In this case, I'm trying to see whether the simulation model will take exactly the same evasive actions or not. So in the top, we have two models. One is single agent, one multi-agent to the right. So let's focus on the three columns to the right, which is the multi-agent, more advanced approach. So in this case, you have the actual trajectories and you have the simulated trajectories. And the three actions are acceleration, deceleration, or no change. And you can see that if you look at the diagonal, it's very high. So we have about 82% accuracy in predicting the right evasive action, whether it is acceleration, deceleration, or no change. Same thing for swerving. We can duplicate the same behavior with very high. And of course, multi-agent models are much better than single-agent models because they are more realistic. They deal with two interacting road users, not assuming that one of them is constant. But this is also very interesting, and I think you will find that interesting. We can even estimate or predict conflict indicator. In this case, we are trying to predict the post-encroachment time. So we are modeling exactly the same near misses and comparing the actual PET value to the simulated PET value. And you can see that we're getting correlation coefficient of 0.85, which is extremely high. So now we have the ability to duplicate the actual behavior of road users, and we can even change one road user, replace a vehicle with an autonomous vehicle, and see how the safety will improve and what are the issues. We can get much better understanding of all the safety issues. So in summary, I think I already 40 minutes. Despite the recent success, the future of road safety is uncertain and faces many challenges. And this is manifested in the reverse and or the increase in fatality rates and injuries since 2005, which is accelerating. Surface transportation, the good news is surface transportation seems to be on the cusp of a new era of smart mobility that can offer considerable safety benefits. And this is the good news. There are considerable opportunities in new technologies, connected and autonomous vehicles, advanced sensing, and edge computing. Actually, edge computing, in my opinion, is one of the most important things that will make a lot of change, because we don't have to process data and send it to the cloud. We can process data on site, which will save us a lot of time to become more real time. We are collecting large amount of data, what we call big data, which will lead to better understanding of road user behavior through advanced AI techniques. We are doing real-time proactive safety management and optimization, which is a total departure from what we used to do for 50, 60 years. And at the end, I would like to emphasize the importance of safety research to prepare us for the future. Thank you very much.